could be letters, numbers, or just things, where every time you select a new thing, you reduce the number of options by 1. And also the order that they're listed in is critical. So we talked about places in a race or officers in a club. There it matters who's president, who's treasurer, or who's first or who's second. Combinations are when you have groupings of objects, smaller groupings out of a larger sample. So if I wanted a committee, so that was an example. If we go back just to remind you what we did the other day, like a lottery game is a combination problem because you can't reuse numbers and order is not important. Sampling, so taking samples of things, the order again is not important, so we would use combinations for this problem 24. Whereas you see something like electing officers or places in a race, you'd say it's permutations. It's just, and it gives you a formula that kind of is easy to evaluate. Ultimately, they all come down to the fundamental counting principle. It's just these two particular things happen often enough where they give them special names and their special formulas. But ultimately, it's the basic thing we're doing, which is counting stuff. Okay, so I was going to talk about just a few more examples. I think the last thing I talked about in the video was maybe this radio station letters where order was important. You ultimately ended up having to use the fundamental counting principle because, in the case of the first letter of a radio station, there's only 2 options. So it's not like you start off with 20 options and then go to 19. License plates, another example. So most, there's vanity license plates, but there are the standard license plate that I know of is you have 3 letters and then you have 3 numbers. So the question is, how many different cars could I license plates could have come up for different cars. If you're designing what kind of lettering to have on a license plate, you want to make sure that it has enough options so that everybody can have a different license plate. I'm sure there's more restrictive rules than I'm going to say, but my rules here is that so these are going to be letters. The first 3 are going to be letters, and the last 3 are going to be numbers. And so so the letters will say letters, the restrictions will say they can be repeated. And so we call that replacement. So if we use an A, we can still use an A. Now for the numbers, I'm going to make up a rule here is no repeats. Okay, just to show you the difference in what happens. Now the order is important in this case because if I had ABC is different than CBA. So for the license plates, order is important. And actually it's easier when order is important because you don't have to divide by anything, you just have to multiply stuff together. So this is just an example of the fundamental counting principle. So when you pick your first letter, you say how many letters are available. I'm not restricting any letters, and I'm not going to restrict swear words or anything like that. So you're going to have 26 choices for the first letter. And because I'm allowing the letters to be repeated, then I don't decrease it by 1. I just say I can use every letter again. And then for the third case, I can use every letter again. So this is like n sub 1 and n sub 2 and n sub 3. And then you can go to the numbers. And what I'm saying here is I don't want to repeat. So when I first choose my first number, I can choose 0 through 9. But because I've specified no repeats, then once I choose one number, I can't reuse it. So then that reduces the number of options in the second choice to 9, and then likewise I can't use anything that I've had before, so I would make that at 8. Now this part is like a permutation because I'm reducing it by 1 every time. This is really neither a permutation or a combination because I am allowing repeats, and once you allow repeats, you can't use either one of them. So, and then so all you have to do is just multiply all these numbers together, and you get the final answer. So I got over here today and I couldn't find my calculator. So there's 2 options. One is in my office, or secondly, I've left it in the last class I've taught in. And usually it's the second one. It's amazing how many times I have left my calculator. It's usually in 385 for some reason. I forget that. So I went back. It's been, luckily, people out here honest. Nobody's stolen my calculator. I've probably done it 15 times in the last couple of years. So it's usually sitting there on the desk, which it was. So if you multiply all these numbers together, you'll get 1, 2, 6, so that's a 1. 1, 2, 6, 5, 4, 7, 2, 0, which is 12 million, almost 13 million. So if you think of a state like Virginia, our population is what? I don't even know what it is these days. It's actually, so with Google, you don't have to wonder about anything. You just have to be curious. My wife gets at me for this because she'll say, I wonder. And I said, I'll check it on Google. And she, oh, God, do you have to check everything on Google? Okay, so it's 8.4 million. So most likely you're not going to have 2 cars per person on average. So that's probably enough, and that's probably why they've chosen that particular sequence. They could get more choices by having more letters and less numbers. Okay. Next thing. Oh, before I go on, so if you've had me before, I mentioned that my family's from England, and I like to mention things associated with it just because they do things differently over there. I was born in England, and I have dual citizenship, so I'm both an American citizen and a British citizen. One time I had 2 passports. I had my American passport and my British passport, and there were 2 reasons for that. Well, 3 reasons. One is just nostalgia, kind of nice to keep that connection. Secondly, this is kind of a made-up one. Is back when I first started having a passport, they used to have hijackings of airplanes, not that often, and they would always say, okay, the Americans, you'd always imagine this thing where they'd say, okay, Americans go over here and everybody else over there, and they shoot the Americans. So I think, oh, I can just pull out with your passport. They don't want to shoot, which was a joke. And the other one is if Britain until recently, they're still technically part of the European Union, but if you have a British passport, you can actually work in Europe without any restrictions. So it kind of opened up. Martha she never wanted to go to Europe, so that was kind of a moot point, but it was kind of an interesting little extra point. Anyway, so license plates in England are not like license plates in the United States. And let me just pull up a picture of one so show you what it looks like. I can't spell. License plates UK. Okay, let's just look at images. Yeah, okay. So that's what they look like. They're all in one row, which ours are too, but they've got the first letter is kind of the interesting thing. Is well, they don't. That must be a European license plate. Anyway, it used to be. I thought it was the first letter of the license plate told you what year your car was. So they would always, instead of saying, "Hey, do you own a 2010 something or other?" If you had a new car, it would be, say, next year would be an N and this year would be an M, and they would refer to your car as by the letter of the license plate, whatever year it is. So that was kind of, and you can go 26 years before you start recycling, and obviously you can tell a new car from a 26-year-old car, so it wasn't like you mistook one car from another. I don't know if this is actually true or not. Age identifier, random letters, area code. I don't know the details. I just know they look different than ours. Okay. So there's probably, their population's a little smaller than the U.S. So, except, they don't have separate license plates for different counties. It's just the same for the whole country. Okay, telephone numbers. So, we have 3 numbers for your area code, and you have 3 numbers, and then you have 4 numbers like that. So again, depending upon the rules that you would use, and there are rules that apply, and again, I don't know what those are, but let's say the first numbers, 3 numbers, you have no repeats and no 0 in the first digit. So no repeats, no 0 in the first digit. The same for the second bunch of numbers. Well, we can have repeats. We'll allow repeats. Yes, allow repeats, and we'll say, again, no 0 first digit. And then in the last 4 digits, we'll say you allow repeats, and we'll say any numbers. So there's no restriction on those. So we start off with the first number, and we say there's no 0 in the first digit. So instead of having 10 choices, I only have 9 choices. I have 1 through 9. Okay, so those are my first digits. Okay. Then I go to the second one, and I say, okay, I can't repeat the first digit. So that means that I have 0 through 9, but one of them has already been used. So I'll still have 9 here. I had 9 the first time because I couldn't have a 0 in the first digit. The second one, I can't repeat whatever I had in the first digit. And then the third digit, you have to reduce it by 1 because I'll have used 2 different numbers for the first 2. So this is not a phone number. This is a number of options. And order is important in this case. I didn't write it down. So again, order is important, just like the previous one. Then the second one, no 0 in the first digit. So I've got 1 through 9. So I have 9 choices. It's going to be basically, except I did say I would allow repeats here. So in that case, for the second digit, I can use 10, and the third digit, I can use 10. I have 10 choices. And then the final one, I allow repeats and all numbers, any numbers. So I'm going to have 10 choices for all 4 numbers. And then if you multiply all those numbers together, you'll get the total number of possibilities. So let's see what that is. 9 times 8, oh, pardon me, 9 times 9, 9 times 9 times 8 times 9 times 10 times 10 times 10 times 10 times 10 times 10. Can they count? 1, 2, 3, 4, 5, 6, 7, okay. And that comes, you multiply all those together and you get 5, 8, 3, 2, 0, 0, 0, 0, 0, 0, which is 5,832,000,000. Okay, so I think that's going to, we're probably not going to have to change our telephone system as long as we allow, we're not too restrictive on the area codes. And that's kind of, back nowadays, it's not as big a deal as it was because people keep their phone numbers. They move to a new place. You don't really know if you have a cell phone. You may have a 540 number, but you may live in New York City and it doesn't make any difference. So that kind of increases your flexibility. Okay, this is a telephone number, another UK thing. Okay, so we'll open this up. Has anybody ever called overseas? You know how to call overseas to a different country? So the way it works is you dial 011. That means international call. So if you were calling from the US, you'd dial 011. Then you have the country code. In the case of England, it's 44. So you dial 0144, and then you dial the number that's the UK number. Okay. So so they've got things like 800 numbers. They call them free phone. So they have a 080. Any mobile phone is 07. So you know if it's a mobile number by that particular prefix. Then after that, so if you dial 01, you don't really need the extra 0 if you're calling from the US, but if you're in the UK, you dial 01. That's basically the original. That gets you in the system. And then depending upon where you live, it may be a 3-digit or a 4-digit number based on where you live. So it's kind of like area codes, but it's not. It's based on more like, as you see here, these are the big cities. And then if you can get to 5-digit numbers, so the smaller the place you're from, the more digits you have initially. And then what they show here is they have, for example, you live in Cambridge, which is where Cambridge University is. You would dial 01223, and then there would be a 6-digit number within Cambridge. It's kind of like our local number, 962 whatever. Now, if you live in a bigger city, you might have a 3-digit number and then a 4-digit number, kind of like we have. And you can so they have all these lists of everybody. So you can all these 5-digit numbers. I'm trying to find where my family's from. There is a list somewhere, which I don't see it. Anyway, it's a little more complicated, but I don't see. Oh, this is right here. So my family's from the nearest big city there. It's not even big. It's called Matlock. So all the numbers that I have would probably be 01629 and then some additional numbers. So you could do the same kind of thing for counting if you wanted to figure out how many options or choices they have. Oh, yeah, and there's another one, a little interesting. Zip codes. You know, zip codes in the U.S. are 5-digit numbers, and usually they're for us. You know, like one's for Clifton Forge, one's for Lowmore, one's for Covington. There's not one for Hematite or things like that. And you've got 5 numbers, and I don't know if the first digit can be 0. I don't think so. Maybe not. So that's kind of easy because it's probably going to be about 99,000 choices because that's the number of 5-digit numbers you have. 99,999. So let me show you this. Just how they do it differently. So what you have is you have letters and numbers. And I don't completely understand the process. For example, let's see if I can look at this picture a little closer. My family's from this area right here. So most of the postal codes have SK and S. Um, and what you can do with the postal code is you can actually put it into a GPS, which they call sat nav, and you put that into your GPS, and it'll put you within a very small location. So where I live in Covington, they would probably have a postal code for my neighborhood, not for the whole city. So it allows you to zoom in. When we went on a trip a couple of years ago, and we went to Wales, and there was this where we were staying. It had an address, but it didn't make any sense. It was in Welsh for one thing, and secondly, I didn't have a map of the city. So I ended up asking somebody at a local store. I said, "Hey, do you know where this person lives?" And they go, "Oh yeah, I know where he lives. You go up this way, blah blah blah." So we got there and still couldn't find it. Now what are we going to do? So there was a police officers that were going around doing something. So I talked to the police officer. I said, "Hey, I don't know where this guy lives." And they said, "Well, we're not from this village, so we don't know we don't know it either." And what he said was, "What is the postal code?" And I said, "It is." So I went back and he says he put it into his GPS and he says, "Oh, it's just follow me." So he drove me. It was about 2 blocks away. And that postal code was close enough to narrow it down to a small number of houses. And then what you did is they didn't have house numbers, they had house names. So it was some Welsh name. And you just went along until you found the person's name of the house, and then you found it. So it does have its advantages if you know the postal code. Okay, again, there's probably some way that you can figure out what the number of options are. Okay, the last thing we're going to do here is just talk about this problem 43. And how many ways could 15 people be divided into 5 groups, where one group is 1 person, one group is 2 people, one group is 3 people, one group is 4 people, and one group is 5 people. And if you take 5 plus 4 plus 3 plus 2 plus 1, you get 15. So we're just grouping them to 5 groups with 5 different sizes. Now, because you're just grouping them together, you know this is not a permutation problem, but is a combination problem. So you just have to think about what happens is you're doing 5 steps, and each step is a combination problem. So the first step is to pick 5 people out of your 15. Okay, so you got 15 people. We're going to pick 5 people. It doesn't matter what order they're in. So to pick your first group of 5 people, you would say, I've got 15 people to choose from, and I'm going to see how many ways I can pick 5 of them. So that's how I would do the first. This is the group of 5. Gang of 5. Okay, then the next step in the process is you're going to pick the next 4 people. Well, now we'll say group of 5 of 15. Now when you pick your group of 4, you're going to pick a group of 4 of 10, because once you've chosen 5 people for your first group, you're only going to have 10 people left to your second group. So what that is 10 things taken 4 at a time. And then you're going to have your group of 3. And these little dots are meaning that the total number of ways I can do it is I have to multiply the number of choices per step. And each step is a kind of a sub calculation by itself. So the next one is you're going to have a group. You want to choose a group of 3 of 6, because again, once I've picked 4 here, there's only going to be 6 left. Then I'm going to pick 2. So this is 6 things taken 3 at a time. And then you're going to have a group of, how many do we have left now? 3. Group of 2. So we need 3 people, group of 3 of a group of 2. I keep doing this wrong. A group of 2. So this is our group of 3. This is our group of 2 out of 3 people. And then you're going to have 1 person left over So this one is, we got 3 left. We're picking 2 people. And then the final one is we have 1 person and we pick 1 person. And each one of these you can calculate using the formula. So you'd have 15 factorial divided by 15 factorial times 15 minus 5 quantity factorial. This one would be 10 factorial divided by 4 factorial times 10 minus 4 quantity factorial. 6 factorial over 3 factorial times 6 minus 3. And this is 3 factorial over 2 factorial times 3 minus 2 factorial. And this one is 1 factorial over 1 factorial minus 1 minus 1 factorial. Now I'm going to cheat and use my calculator to do this because it has it built in. So the point is not to do. We know how to do those, so we're going to that was the wrong button here. Let's try again. Actually, let me clear this. So you can see this is why I don't use my calculator to do this, because I'm not very good at it. So you got a lot of buttons to push. Okay. Okay, so if you do this calculation, you get 3003. Now what we'll do is we'll just change the numbers here. I'll have to re-enter the. So, and then this one is 210. If you evaluate that, and this one is 20, and this one is 3, and this one is 1. I'll explain why this is 3 in a minute. And so you multiply all those things together. So you get to find the total number of ways you can arrange these 15 people. And obviously this is much more difficult than you're going to have to worry about knowing, but I just want to kind of show you how this whole thing, give you a sense of how this works. So you get 37,837,800. So that's a lot of different ways to group the people in this particular problem. Now, the question may be, well, you did 5 first, and then 4, and then 3, and then 2, and then 1, but the problem actually asks 1, 2, 3, 4, and 5. So if I were to do the problem, and instead of doing it this way, if I did it the opposite way, what I'd do is I'd take the 15 people and choose 1 person. And then once I choose 1 person, there would be 14 people left. And I'd pick 2 people from those 14. And then I'd have 12 people left. And I would pick 3 from those 12 people. And then I would have 9 left. 12 minus 3 is 9, so I had 9 people. And I'd take 4 of those for my 4-person committee, or 4-person group. And then finally I'd have 5 people left, and I'd pick all 5 people. And the question you might say is, well, what's the answer? The answer is 37,837,800 if you actually did the calculation. They come out the same, even though it seems like they're very different. I can pick these people in any order. You just have to believe me, because I don't want to spend another 5 minutes doing the calculation. But so this is it's just kind of demonstrating how you use combinations where you have more than one combination kind of stacked together. Okay, so here's your homework for the second. Well, we'll come back to that in a second. Let me go ahead and assign the homework, and we're going to talk about cards. So these are your homework problems.
Did you want to look at the ones that were due today?
If you have it, just turn it in. Yeah, there was somebody who asked about section. Once you've got those copied down, I'm going to put up section 2 homework just in case somebody forgot to write that down. Okay, let's just open up section 2 here so I can make sure anybody who didn't get the homework assignment. So it's this one here. Okay, so if anybody's, I assume you guys have it. If anybody's watching the video, here it is. You can pause it. Okay, so I'm going to ask questions today for the people who are not here. So, what could be the first question I could ask you? So have you ever been to a foreign country, and name one of them? Okay, so that's question 1. There could be more questions coming up, so you need to watch the whole video. So what you're going to do for you guys listening to the recording is you're going to email me, said I watched the video, and here are the answers to the X many questions that I have. Okay, so back to the what we're just talking about. So I mentioned that initially probability had to do with gambling, and card playing is gambling. So there's one thing, you know, some people don't know cards because they don't play cards, and I don't play cards that much either, but I've actually, but you know, a deck of cards has how many suits? 4 suits, and how many cards in each suit? 13, yep. And how many face cards per suit? No, those are the numbered cards. Well, actually, it'd be 4, yeah. So it's Jack, Queen, King, and Ace. Count Ace. So what this is just showing you is here are the cards. There are 13 cards per suit. You've got 2 through 10, Jack, Queen, King, Ace. Okay, and you got 4 suits, so it's going to be 4 times 13, which is 52. There's 52 cards. That's why they call it 52 card pickupper, you know, which is just picking up, throwing the cards on the floor and picking them up. Okay, so there are different card hands if you're playing poker, 5-card poker. So you deal out 5 cards, and you put them in your, you know, look at them, and usually you order them into pairs or threes or maybe some order, maybe not. But the order doesn't really matter. You just order them for convenience. It's still the same 5 cards. So all the calculations for card hands involve combinations, not permutations. And they are, you know, there's different more and less probable hands to get. So the most difficult hand to get is called a royal flush. And a royal flush, there's a straight flush, and there's a royal flush. And a royal flush actually is 10, Jack, Queen, King, Ace. So there's the 5 highest cards, and they are the top 5 highest cards. So there's 4 royal flushes out of the possible hands in a deck of cards. In that case, that's really not using combinations. It's just realizing that, you know, for each suit you can have 10 Jack, Queen, King, Ace. Okay. The next one is a straight flush. What that means is you just have 4 cards that are in a row. So 2, 3, 4, 5, 6. That's a straight flush, and they're all in one suit. And then you have So I'm not expecting you to memorize all. Then you get down to the least winning hand is you get nothing that matches. Or there's no combinations, and you would, if you had two hands that there were no pairs, say pairs the next to least likely thing. You get two numbers that are the same, or two anything that are the same. If you don't get anything that's the same at all, and there's no sequence to them, you would, I guess, have the one that has the highest card. If I had a king and the other person had an ace, then the person with the ace wins. But a two of a kind would always beat anything that has no matching whatsoever. So I'm just going to show you something online I was looking at today. I guess I search for Google here. Card hands, Wikipedia. I think I'm in my phone. I probably need to turn that thing down. Okay, poker probability. Okay, so what they do is they show you all the different kinds of hands. Royal flush, 10, jack, king, queen, king, ace. There's one per suit, so there's 4. If you actually, the easiest thing to do for figuring out the number of card hands is just to use what we know. So if you're just picking 5 cards, and you can't, there's no repeats, so these are cards. When you choose the first, the number of options for the first card are 52. And the number of options for the second card are 51 because you've already used one of the cards. And likewise, so you just have this. Now, but order isn't important here. So this would be if order were important. So what we would do is we divide by 5 times 4 times 3 times 2 times 1. That's how many ways 5 cards can be arranged, but still be the same 5 cards. It's also 52 things taken 5 at a time as a combination. So, however you want to evaluate this, what the formula would be 52 factorial over 5 factorial times 52 minus 5 factorial, which would be 52 times 51 times 50 times 49 times 48, 1, 2, 3, 4, 5 times 47 factorial, divided by 5 factorial. 52 minus 5 is 47, which is, once you cancel those out, it's the same as we had up there. So let's just plug those in there and get the number. So you get 52 times 51 times 50 times 49 times 48 divided by 5 times 4 times 3 times 2 times 1. So you get 2,598,960. Those are the number of possible card hands that you can be dealt with 5 cards. And 4 of those hands are royal flushes. So if we go back to Wikipedia here, and we go down to, you can see the odds are 1 in 649,730, much better than the lottery. But if you go all the way down to the bottom here, which is the total number is 2,598,960, which is exactly what we got here. Okay, so that's the easiest number to get for cards, to figure out what are the total number of possibilities. And so to find the odds or find the probability, all you do is take the number of possibilities divided by for a given hand divided by the total number of hands. That gives you the percent chance of getting that particular hand. And it's pretty low. I mean, if you look here, for the royal flush, which is the most difficult hand to get, it's the probability is 0.000154%. And if you look at this list of each card hand is shown, and it tells you what the odds are, the probability and the odds. There's 2 numbers there. What's the first and second? Probability, cumulative probability. Okay. So this is one we want to look at. The probability of getting the hand is that. And then these are the odds. And these show you the way to calculate them. And what this means is 10 things taken one at a time times 4 things taken one at a time minus 4 things taken one at a time. So these descriptions are all using combinations. It's just different ways. And it's not obvious why they use these kinds of, why they multiply these numbers together. So I'm going to show you one particular case, and you can always look at that if you're ever interested. But so we're going to look at the case of a pair. So how many of those 2,500,000 hands are pairs? Because that's the most likely thing to get. That's actually. So the way you do it is you think about a pair. So if you pick a number like 2, you can do the 2 of hearts and the 2 of spades. You do the 2 of hearts and the 2 of diamonds. It doesn't matter what the order is. So it's a combination problem. So I'm taking 4 cards, all the 4 different 2s, hearts, diamonds, spades, clubs, and I'm picking 2 of them. I'm saying how many different ways can I choose those? So that would be, so to pick the 2 cards that are going to be the ones that I'm going to have as a pair, there are that many possibilities. Okay. Now, you can do that. That's assuming like any number, 2 or 3 or 4. But we have 13 different numbers. We have 2 through 10 plus Jack, Queen, King. So we multiply that by 13. So this part is only talking about the pair. Then what happens is you've got the rest of the cards. You got to take into account how many ways can I have the other 3 cards. Well, you can't include the number that you've already chosen because then you'd have 3 of a kind. So we have to eliminate that. So we're only going to have 12 cards to choose from that are remaining. The 12 that are not the one that's the pair. So if I got 2 2s, these are the cards. So if I got a 2 and a 2, I can't use 2s over here to count. So I'm only going to have 12 cards to choose from, remaining cards, and they're going to be pick 3 at a time. And that's it. Okay? So first you figure out I've got a pair, which suits am I going to have in my pair? Then I'm going to say, well, then I also have 13 different cards that can happen to, and then I take the 3 remaining cards, and those 3 remaining cards can only be one of 12. Can't be the one that's already been used. So if we did this, you would get, again, I'm going to use my calculator to give me the numbers. So if you take 4 things, taking 2 at a time, that's 6. So you take 6 times 13. And then if you take 12 things taken 3 at a time, combination-wise, you get 220. And you multiply those together, and you get 6 times 13 times 220. And that seems low. So what did I mess up here? Oh. It shouldn't be 12 because we have 12. We really have 48 cards because I'm going to take 4 out of play because I can't use the 2 that I've already chosen plus the other 2 numbers that I can't use because then I wouldn't have 2 of a kind. So it's really 48 things taken 3 at a time. So that number was too low, so I know I did something wrong. Okay, so 48 things taken 3 at a time. So hopefully this is right. Okay, so you get 17,296. So you take that times 13 times 6, and you get 1,349,088. Okay, so let's just check, see if I did that right. So if you go down here in this Wikipedia entry, one pair, 1,098,000. That didn't seem, that's not quite right, is it? Okay, so I did something wrong. Let's see what I did wrong. 4 things taken 2 at a time. 13, no, those are right. 12 things taken 3 at a time. I thought I had that figured out. Okay. Needless to say, I didn't, these are not completely obvious how to do, so I didn't do it right. That's okay, because you're not going to have to learn how to do this anyway. But, it's just kind of interesting that's you basically, the basically one thing I want you to get out of this is that for card hands, you use combinations, and the way that you do it is not always completely obvious. It's obvious for the total number of choices. That's an easy thing, 52 things taken 5 at a time. But when it comes down to the other options, you can see they get fairly complicated, and it's sometimes you don't understand it initially. So there you go. I didn't understand it. I'll think about it. I'll talk to you next time about it. Okay, so that's it for section 3. Section 4. By the way, the test, when is the test? Not next week. Well, I got to the end of class and realized I hadn't asked you another question, so here's another question for you. So we were, what the heck were we talking about? Cards, yeah. So a lot of people don't play cards these days, so I'm just doing a little survey. So do you, say on a scale of 1 to 5, meaning 5, I know I'm an expert at cards, and 0, I'm a dunce at cards. Where would you put your understanding? So when you talk about 3 of kind, full house, do you understand what that means or not? Just curious. So there may or may not be another question. I'm not going to let you know. So if you get to the end and there is a question or not a question, just let me know. Next week, probably Wednesday of the following week. So next week's this week, so it's probably going to be the 31st of January-ish, just so you can plan. Okay. Okay, so section 4, using Pascal's triangle. So Pascal's triangle is a way of coming up with the numbers from the combination equation without having the equation. So I'm going to demonstrate how you generate Pascal's triangle, and then we'll look at the numbers and see how those compare with the combination formulas. Okay, so that's what we're going to do in here. So you start out with 1 at your top entry, and it's going to look like a triangle. So the first row is 1, the second row is 1 and 1. Okay. The third row is 1. So you always start with a 1 and end with a 1. Now here we had one item, 2 items, so we need another item right here. And the way you find the value here is you go back to the previous row and look diagonally from where you're trying to, so you're trying to find something to put in here. So what you do is you take this number, which is 1, and you take this number, which is 1, and you add them together, and you get 2. Okay, so let's do that for the next row. So again, we're making a triangle, so you have a 1 here and a 1 there. So I need 2 entries there because it's the 4th row. So what I said was you go to diagonally up this way, which is 1. You go diagonally this way, which is 2. You add them together, and you get 3. And you do the same thing on this side. So you get a 2 from here and a 1 from there. You add them together, you get 3. Okay, let's do another one. So this has 5 entries, so we put a 1 here and 1 there. So we need 3 things to go in there. So you go diagonally here, which is a 1. You go diagonally here, which is a 3. Add those together, you get a 4. Here, diagonally to the left is a 3. Diagonally to the right is a 3. You add those together, you get 6. And then finally, you get a 3 from there and a 1 from there. Add them together, you get 4. So I'm just going to do the next couple of rows here. Put the 1s on the end. And now I know what I'm doing. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. So let's do one more. So we put the 1s out here again. 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. 10 plus 5 is 15. 5 plus 1 is 6. So you can just keep going on for as long as you want to. That's called Pascal's triangle. So what does that have to do with what we're talking about? Well, if I drew a triangle like this, let me make sure I do this right. That's not what I want. Okay. Yep. So what I'm doing is I'm making a triangle. Instead of with numbers, I'm using these subscripts. I think one thing we haven't talked about yet is, what is x things taken 0 at a time? Because how do you pick 0? Well, it's kind of like 0 factorial. 0 factorial is 1. And any number taken 0 at a time is 1. So it's sort of the same rule. And that's why all of these things down here are 1s. So you can, if you look at the corresponding numbers in your Pascal's triangle, you can find the corresponding values for the combinations of this many things taken at that many times. You'll also notice, I said these are all 1s because they're all taken 0 at a time. This outside one is also 1, and that's because anything, if you have one thing and you take it one at a time as a committee or as a grouping, there's only one way to do that. And likewise here, if you have 2 people and you stick them together into a 2-person committee, there's only one way of doing that. So these are always 1s. So anything where these 2 numbers are the same is always 1. So I guess the way of doing that is you would say C sub n equals 1. So anytime these 2 numbers are the same, if they're 1 thing taken first 1 at a time is 1. 20 things taken 20 at a time is 1. So these are all. So that's kind of that's the other side. This represents this side. This represents that side. And then you could, if I actually write these numbers, you can say this is equal to 1, 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 this is equal to 2, so I'm going over here, 2, this one's equal to 1. So I go to the next row, I've got 4 elements, so it's going to be 1, 3, 3, 1. So this is equal to 1, this is equal to 3, this is equal to 3, this is equal to 1. So let's do one more row here. So if you take 4 things 4 at a time, then you go 4 things. So the first number is the row, and the second number is the kind of going for opposite direction. And we start with 0. So there's 5 in this row, so 5 elements. 4 things taken 4 at a time, 4 things taken 3 at a time, 2 at a time, one at a time, 0 at a time. So what do you think the numbers should be here? Just looking over at the corresponding row out of Pascal's triangle. So this was this row. So I look at the next row. I got 1, 4, 6, 4, 1. So there'll be 1, 4, 6, 4, 1. So if you had a sheet of paper with a big Pascal's triangle on it, you might not even need your calculator to do the calculations. You just look them, you look at the corresponding number in the Pascal's triangle. So that's it. It's kind of interesting. For the most part, you'll still just use the formula, but but interestingly enough, these numbers actually have some significance beyond this relationship between combination number and the value in the triangle. So I want to explain that one. So other applications, that's under title of other applications. This is something you learned in Algebra 2 if you took Algebra 2. Hopefully you did. So this is called a binomial. It's just, like x plus 3 when you were factoring stuff, that would be a binomial. And, in Algebra 1 and Algebra 2, you learned this. If you had a plus b times a plus b, use FOIL, and what you'd end up with is a squared plus ab plus ab plus b squared. And that's because you do first. So FOIL, let's write FOIL out, F-I-O. So you do first, which is this term, and then you do O, which is outer, so you do these two terms. So A times B, which is this one. So this is F, this is O. I is inner, so you do B times A, which is still AB. So that's the inner, and B times B is the last. So that's FOIL. And you can then simplify that down by adding these two terms together because they're the same. So you get a squared plus 2ab plus b squared. So if you wanted x plus 3 squared, x plus 3 times x plus 3, you could use this formula to get the answer without using FOIL. You just do this is a and this is b. So you'd have x squared plus 2 times 3 times x. So it'd be 6x plus, then you square that, you get 9. Okay. Then, then you could do a plus b times a plus b. Never went beyond this, I think, in Algebra 2, but that's turns out if you multiply that out, you get a cubed plus 3a squared b plus 3ab squared plus b cubed. Anybody remember seeing that? It's called a trinomial. If you take the way you'd show that is a plus b cubed. And there was this formula that told you to do that. Well, notice if you go back over here, 1, 3, 3, 1. Those are the numbers corresponding to this row, and the coefficients in front of here, 1, 3, 3, 1. The second row we had 1, 2, 1. 1, 2, 1. So you could use Pascal's triangle if you wanted to do a plus b to the 5th power. Instead of multiplying this thing out and having to do it the long way, you would be able to use the I'd have to go one more row. You could use this row because this is squared cubed to the 4th to the 5th. So you'd have 6 terms, and you'd have these as your coefficients in front of it, 1, 5, 10, 10, 5, 1. So I'm going to write that just to show you how it works. So you'd have a to the 5th plus 5a to the 4th b plus 10a cubed b squared plus 10a squared b cubed plus 5ab to the 4th plus b to the 5th. That sure beats multiplying that thing out. I mean, it would take you probably 20 minutes to multiply that out and use FOIL and stuff. So it's kind of interesting, these coefficients correspond to the numbers for combinations. So that's another application of the Pascal's triangle. Now most of the homework problems in this section are basically combination problems because this Pascal's triangle has to do with the combination formula. So do you have to use Pascal's triangle to solve the problems in this section? No, not really. Just if you want to, you can, but if you just want to use the standard formula, if you wanted to know, 5 things taken 2 at a time where the order is not important and you wanted to use, the formula n factorial over r factorial times n minus r factorial, that's fine. I'm not going to force you to use the Pascal's triangle. It's just more interesting. It's kind of an interesting math thing. I didn't know about it till I taught this class, so I find it interesting. But then again, and in your book you'll see it. This is basically filled out to the 10th row. So what you could do with the stuff in the book is you could 10 things taken any number of times from 10 to 0, you could just look them up directly off of this table instead of having to use the formula. And here they just show it to 7, say that's the pattern. So let's just show you how you would do it. If I wanted to know what are the number of arrangements of 5 things taken 2 at a time, all I'd have to do is I would go to Pascal's triangle here. So here it is, and you take the 5th row, and you start here, and it's 5 things. This is 5 things taken as a group. This is 4, 3, 2. So you'd read that number off, which is 10. So then you get the number without having to use the formula. If you wanted to find out what the value of this was, 9 things taken 4 at a time, you'd go to row 9, and you'd go 9, 8, 7, 6, 5, 4, and you'd read that number, which is 126. And then 7 things taken 5 at a time, you go to row 7, and you'd go 7, 6, 5, and that would be the number. Or you could go the other direction, 0, 1, 2, 3, 4, 5, you get the same point. So you either start this side and count down, or this side and count up. So that may be the only, you might have to do that as far as just proving that you can actually do it. Okay, so let's just look at another committee problem here. And I put a problem like this on the test involving congressmen. So it says a committee of 4 congressmen will be selected from a group of 7 Democrats and 3 Republicans. Find the number of ways of obtaining each result. So it's asking how many different committees can I get if I have exactly 1 Democrat. So this is a 2-part process because I'm going to choose a Democrat and then I'm going to choose Republicans. So it's like these previous problems where you figured out a number for the first part and a number from the second part. And each part uses a combination thing. So you look at it and you think, okay, I've got 7 Democrats and I want to have exactly 1 Democrat on that committee. And there's 4 people on the committee. So the first part of the process would be to take my 7 Democrats and pick 1 of them. So that's the appropriate combination expression. Then the second part, if I'm only going to have 1 Democrat, how many Republicans are going to be on the committee? So read the problem. Pardon me? So right, yeah. So you had 4. One of them's a Democrat. That means because 4 minus 1 is 3, that means when I say exactly 1 Democrat, that implies exactly 3 Republicans. It doesn't say that, but it is, because I'm Republicans. Okay. So the second part of the process is picking a Republican. So again, it's a committee, and I have I have 3 Republicans on the committee, and I have 3 Republicans to choose from. So the second part would be 3 things taken 3 at a time. Now you could use Pascal's triangle to figure this out. But if you go back over to Pascal's triangle, you'll notice that all the ones taken 0 at a time are 1, and all the things taken the same number are 1 also. But the next ones in are always the number. If you look down here, this is say row 3, 1, 2, 3, 4 elements. You'll notice that 3 things taken 2 at a time is oh, they actually drew that in a different order, but anyway, it doesn't. So here's let me just write the rule out and explain it. So let's say you have n items taken 1 at a time. That's always equal to n. So let's show that. So if you have 3 things taken 1 at a time, that's 3. If you have 7 things taken 1 at a time, that's 7. If you have 25 things taken 1 at a time, it's 25. So when you always just when you take 1 thing at a time, this number is 1. The answer is always the first number. Okay. The other thing is if you take 1 less than this number. So on the other side of the triangle, you would have 3 things taken 2 at a time, 7 things taken 6 at a time, 25 things taken 24 at a time. So here I have 1. Here I have this minus 1 is that. 7 minus 1 is 6. 25 minus 1 is 24. So the other this says n things taken n minus 1 times. So these are examples of this. That's also equal to n. So that's 3. That's 7. That's 25. And that happens a lot. You see this where you have 1 thing taken, 1 person chosen from the whole thing, and it's always just the first number. So using that, 7 things taken 1 at a time is 7. I don't even have to use Pascal's triangle. And anything taken the same number, either this or if I did 3 things taken 0 at a time, these both have a value of 1. So the answer is 7. 7 times 1. So it just saves you time. So there's 7 committees. 7 different ways you can put a Democrat on there. There's only one. When you have 3 Republicans, there's only one way you can put all 3 Republicans in a committee. So that doesn't increase the number. So let's say you have exactly 2 Republicans. That also means exactly 2 Democrats. So using the same kind of thought processes, I'm going to pick 2 Republicans. I've got 3 Republicans. So you have 3, you're going to choose 2. So that's the Republican part here. And then you multiply by the second one. Well, I have 2 people on my committee, and I have 7 to choose from. So that would be the equation that you'd use. This is 3 because this number here is 1 less than that, so that allows me to use one of this rule here. This one is not so simple. You might use the formula. So I'm going to use the formula. So 7 things taken 2 at a time is going to be 7 factorial over 2 factorial times 7 minus 2 factorial, which is 7 factorial over 2 factorial times 5 factorial. And then I write 7 factorial is 7 times 6 times 5 factorial. What that does is allows me to cancel those 2 out. And if you multiply the rest of it, you get 7 times 6 divided by 2 times 1, which is 21. So the second number here is 21. So the first part you have 3 choices, the second part you have 21 choices. You multiply those together, you get 63. So the answer is 63. So the key thing here is doing these two-part problems involving Republicans and Democrats. You're going to have one is choosing the number of Democrats, one part is choosing the number of Republicans. You typically have, say if you're dealing with Congress, you're going to have a total of 432, I guess it is. And then you're going to pick a smaller number of that, maybe 4 or 5 people of each party to be in the committee. So it's a little more complicated. And we'll look at it some other time. For right now, that's all. Let's see, I'm trying to remember what. Okay, yeah, I don't have a whole lot. We've already talked about that, so we're not. Actually, we're pretty close to the end here. It's 2:13. Let me just introduce this problem, and then we'll work on it next time. I'm not going to assign the homework yet. So this is a problem that's in your book, which is kind of difficult to understand if you read it. So it's saying if you have a coin and you can either toss a fair coin 5 times, or you can toss 5 fair coins once each. Okay, this gives you the same result. It gives you heads and tails. And we talked about this using a tree diagram. And if you list the different ways you can have these arrangements, so the different arrangements are you can have exactly 0 heads, exactly 1 head, exactly 2 heads, exactly 3 heads, exactly 4 heads, and exactly 5 heads. Those are the choices. And if you just use the listing method or the tree method, here are all the different possibilities. So there's only one way of getting 0 heads. That's to get all tails. And there are 0 ways to get 5 heads, which is all heads. And then in between, you can see all these different combinations. If you want to have 1 head, you can get it. You can get it during the first toss, the second toss, the third toss, the fourth toss, fifth toss. So there are 5 of those. If you do it for two heads, here are the possibilities, and you count those up, you get 10. And if you have 3 heads, you can see all the list here, and you end up with 10. 4 heads, that's the same as 1 tail, so you can have the tail last, next to last, in the middle, second, first place. So it's kind of like this, except the opposite. There are 5. And you can see these numbers are just the numbers in the row of combinations in Pascal's triangle. 5 things taken 0 at a time, 5 things taken 1 at a time, etc. So that's another place where that pattern of numbers is useful. It allows you to figure out, the number of different ways that, in this case, order is important. So to find, if I want to find the total number of possibilities, I would probably use, well, actually what I have to do, because I'm allowing repeats, I just have to take 2 to the 5th power, which is 32. So there's 32 possibilities, but total possibilities. But to do them in these groupings of 0, 1, 2, 3, 4, 5 heads, the numbers turn out to be just the values of the combinations, even though it may not look like a combination problem. Initially this doesn't look like a combination problem because I'm not picking, I don't have 5 things and I'm taking 2 at a time where order is not important, because it looks like order is important here. So it's just telling you that there are other cases where the combination formulas can give you the numbers you need. And the purpose here is, which I'll talk about next time, is how you have to look at this problem so you understand why they're using combination formulas. It's not obvious initially why they work. You just say, oh, they work. So but why do they work? So I'll try to explain that. Okay, so that's it. Thanks for coming in. Roughing the, did you have any problem at all? Yeah. Now about 10 o'clock the plow came through and put some